Yes, ma'am, it's been started.
Okay, thank you. This slide, then we will start. So I hope my slide is visible in PPT mode uh, with 6 to 13 points for design procedure of plate. Is it visible?
Yes, ma'am.
Okay, okay, thank you. So in the last class we have started the discussion on plate contactors, and in detail we have discussed that what conditions, what situation may be possible during the operation, and what we need to um, uh, fix that, what we need to um, the method, the parameter which we are considering, that should not be violated. Okay, so if you recall, we have discussed three different trays: a sieve plate, bubble cap tray, and valve tray. Bubble cap is has widest, what we can say, range of flow rates it can handle. Okay, in comparison to valve tray and then sieve tray. And valve tray is better than sieve plate if lesser flow rate we are considering. But the point is, when flow rate is less, no mixing exists. Okay, so for lower system, so for that plate design, we need to consider different parameters, and that we have already discussed. And when we compare sieve tray and valve tray, sieve tray is much more simpler and cheapest in comparison to valve tray, and the functioning of each type of tray we have discussed. Okay, and if that operating parameters are such that it can be done with the sieve plate, we should always refer that. Okay, until unless you can, you are not advised uh, to operate at very low flow rate. Okay, then we can go for bubble cap, and the operating range of parameters are more more in valve tray in comparison to sieve plate. Okay, so in that way we have discussed, and then we have discussed the liquid flow pattern over the plate, and after that we have started discussion on plate hydraulics. Okay, so in plate hydraulics we are discussing the plate design, and the design is a bit complicated because you need to adjust so many parameters within the permissible limit. Okay, so this is the procedure, and this is the operating range when we are considering. Okay, so if you consider the weeping condition will occur at low vapor rate and low to high rate of the liquid. Okay, but it is more it depends more on vapor flow. Okay, so that is the weeping condition. And if I am having the higher liquid flow rate and vapor flow rate will keep on increasing, we have downcomer backup. Okay, downcomer backup is there, which has a particular limit, and if we are not going to uh, adjust this, we can have the flooding condition. Okay, you see, flooding condition will occur at varying flow rate of liquid from from low to higher. Okay, but flow rate, when we considering vapor rate should keep on increasing, then the flooding will occur because it pushes the liquid upward. Okay, and we have entrainment also. What is that entrainment? That when vapor comes in cross flow with the liquid, and when it is going above than the tray, so it takes some of the liquid droplets. Okay, so you can understand that entrainment will occur first, then the flooding. Okay, and this coning, we all have discussed that when liquid flow rate is very low, okay, and vapor flow rate will keep on increasing, vapor will pass through the liquid without having any interaction, and that is called as coning. So if you consider all these nine, in between I should operate. Okay, so during the design we should check entrainment, we should check flooding condition, then downcomer backup should be sufficient, and weeping condition we should check. Okay, so in that way you can consider the you can identify that what parameters you need to address more precisely or more accurately in comparison to other, like weeping condition, backup is there. Okay, downcomer backup is there, and excess entrainment and flooding. We don't consider this coning because if you see below that vapor, the flooding will occur. Okay, so uh, if I fix the flooding, okay, the uh, up to here, the what we can say, the vapor flow rate can be fixed, and the vapor when it is moving upward, okay, moving upward, then we can have the coning condition, and this coning condition is more precisely for low liquid flow rate. If you see, the range on x-axis is only this much. Only this much. Okay, so that liquid rate should be less. If liquid rate is less, okay, and vapor flow rate is higher, we can have the coning condition, but that we do not check, but because before that we have already checked the flooding condition, so that is the thing, coning is difficult to occur. Okay, and if you see the flooding rate, flooding condition, the vapor liquid rate is much more, okay, in comparison to this. Okay, and therefore usually coning condition we do not check, but that you should understand when you are dealing with low flow rate of liquid. Okay, so this is the operating range, and now we will see the parameters which we have discussed, or steps which we have discussed in the last class for design of plate, one by one, all these parameters. Firstly, we will calculate the diameter of the column. Okay. When we consider the diameter of the column, the in this diagram again, this diagram, if you see here, I am having the flow rate, okay, for flooding, and here I am having the flow rate for weeping. Okay, now the point is the vapor velocity will be maximum when flooding we consider. Okay, I hope you are getting my point. So the upper limit of the vapor rate will be fixed with the flooding condition, and lower limit we can fix with the weeping condition. Okay, so when we consider the diameter, because diameter will depend on the vapor flow, and how much how much part of the tray will be covered by the vapor. Okay, so if vapor flow rate would be high, okay, if vapor flow rate is what we can say very high, then in that case it will cover the whole diameter or complete plate. Okay, therefore flooding condition, because when the vapor flow rate is too high, flooding will occur. Okay, so what is the flooding, what is the velocity at which flooding will occur, that we need to calculate, and based on that we need to decide the vapor velocity, how much vapor velocity should be there. So flooding condition fixes the upper limit of vapor velocity that we have discussed. And secondly, a high vapor velocity is needed for high pressure efficiency, and velocity will be normally be between 70 to 90% at which flooding will occur. Okay, because obviously when I'm having the flooding condition at maximum flow rate, the operating flow rate should be lesser than that value at which flooding will occur. Okay, so that we will always remain in a feasible range. Okay, and flooding can be avoided completely. Okay, so the point is, whatever velocity of vapor uh, at which flooding will occur, the actual vapor velocity should be 70 to 90% of that at which flooding will occur. I hope you are getting my point. So first of all, we will calculate the velocity at which flooding will occur, and then we can have that, like between 70 to 80% of that velocity, we can have the vapor. This is the complete range, 70 to 90. However, for design purpose, we recommend, we, we are recommended, okay, we are recommended around 80 to 85% of flooding velocity. Okay, I hope you are getting my point. If any observation is there, you please share. Okay. So in that way, what we can say, that complete vapor velocity at which flooding will occur, the normal vapor velocity or operating vapor velocity should be 80 to 85% of that. Okay. Now we will see how to find out velocity at which flooding will occur. So, the velocity at which flooding will occur, it is empirically related by this expression depending upon the density of liquid and vapor, and this K1. K1 is a factor, or we can have a constant, and UF is the velocity at which flooding will occur. So flooding vapor velocity we usually call it. Okay, K1 is the constant. How we consider the K1? Okay. So if you see, this is the diagram, this is the graph which is given in volume 6. And this is belong to chapter 11. Okay, all heat exchanger, condenser, reboiler, all are available in chapter 12, and here we need to recommend chapter, we need to consider chapter 11. Okay, so it will depend on FLV, and if you see here, I am having different curves for plate spacing. Okay, so if you recall the last class, there we have discussed that first we need to decide this plate spacing, and then we will proceed towards the column diameter. You can refer the steps which we have discussed yesterday. Okay, so that usually plate spacing varies from 0.15 to 1. Okay, but here value is given only up to 0.9, and in between you can take the value. Okay, so usually we consider like 0.45 or 0.5 as a what we can say feasible plate spacing. Okay, and it will depend on this FLV, and this FLV is basically liquid vapor flow factor. Okay, liquid vapor flow factor. How we can find it? We can find this by this expression, that is FLV, which is equal to LW by VW, and root over rho V by rho L. Okay, LW and VW, these are the flow rate uh, per unit area. Okay, so if you consider this LW as well as this VW, both are having the same unit, so that will be cancelled out. Okay, or in other word, if it as it depends on the area, so area is same for liquid as well as for vapor both. Okay, therefore because we do not know the area so far, so we will consider LW by VW as L and V only. So it is basically liquid mass flow rate. Okay, sorry. Okay, this is liquid mass flow rate and vapor mass flow rate. The values are already given. Okay, but it depends on the that area also. Okay, but you need to decide based on the mass flow rate and root over rho v by rho l, that you can see for FLV. Okay, once you know the FLV, you can find out this K1 factor. Now here I would like to mention one uh, condition that when we consider the design of distillation column, when we consider the design of distillation column, uh, it has two different regions. Okay, that is rectifying section as well as uh, stripping section. Okay, or above feed or below feed. Okay, so this diameter will depend on the what we can say, depend on the location where plate is available. Okay, because if you consider LW and LW and VW, these flow rates are different for rectifying section and for stripping section. Okay, so you may have different FLV value. Once you have different FLV value at top and bottom, that is the only possibility. Okay, at top and bottom this flow rate differs, and therefore FLV value you can have different value at two locations, and corresponding to two FLV you can have for the same spacing, you can have two value of K1. Okay, so once uh, you have two values of K1, you can have two values of flooding velocity also. Okay, so for diameter, all calculations will be considered based on location. Okay, all calculation means which we are conducting for diameter. Okay, otherwise for which case it should not depend on the location. Okay, that we will see. Okay, so flooding velocity UF will be calculated for top and bottom both, and yes, I hope you are getting my point. The diameter is the only parameter. Okay, diameter is the only parameter for which top and bottom, above feed or below feed, the value differs. Otherwise, all other value which we are going to discuss, it will be location dependent only. Okay, so that all other calculation will be done depending upon the location of the tray. But even if you know the location of the tray or plate, you need to calculate diameter at above section and below section um, in both way, and whatever would be the higher diameter, that we need to choose. Okay, so in that way you can consider, because you know that column diameter, when I am considering, the diameter is same at top and bottom both. Okay, so we need to calculate the diameter for above and below section and choose the higher one. Okay, so I hope you are getting my point. Another point is, when I am considering this particular graph, and this graph has been given by experiments. Okay, so the K1 will depend on certain conditions. Okay, what these conditions are, let's discuss. The condition is hole to active area is 10%. Okay, for other ratio, apply the following corrections. Okay, so when we have considered this particular graph, so hole to active area is 10%, that has been considered while performing the experiments. Okay, if I'm having other ratios of this, I hope you are getting what is hole by active area. Okay, so hole is not a single hole, that is all hole. Okay, and area of all hole divided by active area should be 10%. Okay, so here you can get the idea that if I'm having the complete metal sheet, how much area we are actually devoting for holes. Okay, so 10% is the higher value. Okay, so when I'm having different other what we can say ratios of whole area to active area. Okay, if 10% is there, nothing you need to consider. If 8% is there, you need to consider K1 value with correction factor, that is 0.9. K1 value which you have already seen from the last graph. Okay, similarly 6% if it is having, we need to consider 0.8 as a multiple or correction factor for K1. Okay, and this will happen for both top and bottom. Okay, doesn't matter. And another condition is, like when the experiment has been performed, the liquid surface tension has been taken as 0.02 Newton per meter. For other surface tension, sigma should be multiplied with that K1, the value of K1, that we need to multiply by this expression, sigma by 0.02.2 power. Okay, so in that way you can consider different correction factors for K1. Okay, so if you can say that K1 is not involved in velocity parameter as well as in FLV value, right? But whether it is dependent or not, you need to take the correction factor for K1, right? Now once I'm having this K1, we need to calculate the flooding velocity and take around 80% or 85% of that as vapor velocity. So by now you have the vapor velocity at top and bottom. Okay, I'm not talking about flow rate, please don't get confused. We are talking only about the velocity. Okay, now to calculate column diameter, an estimate of net area AN is required. Okay, so here I'm having this cross section of the column, and this is a plate. वो मैंने सर को बता दिया था. I will join after some time. So we have this plate. Okay, and you know that in the plate the holes are available in perforated area, which is again lesser than the active area. Okay, active area is when I am having this this chord and this chord. Okay, so whatever the area is available in between, that we consider as the what we can say as the active area. Okay, net area will be only the area of a single plate. Okay, so you can understand, you can argue over here that we are considering the vapor velocity and which supposed to move through holes only. So why we are not considering active area and we are considering net area here? Okay, the thing is because some calming zone is already available, but it is not like vapor cannot be controlled. Okay, vapor can be controlled only in the downcomer section where liquid is available, so vapor will not move there. However, vapor will cover the whole plate. Okay, though it passes through the holes only. Okay, but my point is when vapor is coming from the bottom, it covers the whole plate area and then it finds its way through the holes to move upward. I hope you are getting my point. Okay, so we need to calculate the column diameter based on net area. Okay, so and net area is this area, right? So how we will calculate the diameter of the how we will calculate the net area? because that net area is again dependent on the, it depends on the column diameter, right, or column area. Okay, so what will happen over here, you have the vapor flow rate, please consider it flow rate. Okay, vapor flow rate at top and bottom both. Okay, and your vapor velocity you already know which is available at top and bottom. Okay, division of these two will give you the area. Okay, flow rate that is given in mass, but you can convert that into volume. Volumetric flow divided by the velocity, it will give the area. Okay, and that area is nothing but this net area. Area of a plate. Okay, that is the net area. Okay, now if I ask you that how you can calculate the column diameter or column area. Okay, column area would be okay, column area includes net area as well as downcomer area. So next step is we need to fix the downcomer area percentage. Okay, so usually it varies from like it can be done, it can be increased up to 15%. Okay, but 12% is a reasonable value to start with, so we will consider 12% of 12% as downcomer area. Okay, now if this is the net area, right, and this is 12% is the column area. Okay, so net area is available only in 0.88, only in net area is available with 88%. Okay, 12% of total area is downcomer area, 88% of total area is the net area. Okay, so you already have calculated net area over here, that you can divide by 0.88, it will give you the column area. I hope you are getting it. Okay, it will give you the column area, and once you know the column area, you can find out the column diameter. That is not the issue. But all these uh, upper, what we can say, upper flow rate, sorry, upper region as well as lower region, like enrichment section as well as the stripping section. Okay, so we calculate the diameter for both, and whatever case diameter, more diameter we obtain, that we consider as the column diameter, right? Just 1 minute, I will start. Yes. So in this way you can find out the diameter of the column. Okay, from here onward, whatever calculation we will do, that will depend on the location. Location means in the problem you will be aware that for which location you are calculating. Okay, either top and bottom, but diameter is independent to that condition and other parameters will be location dependent. Please keep in mind. Is to decide the liquid flow arrangement, and liquid flow arrangement you can see from this graph. And arrangement we have discussed, right? Single pass, reverse flow and double pass, all three we have already discussed. And here you have the liquid flow rates, and this liquid flow rate will be of that region where plate we are going to design. Okay, either enrichment or a stripping section. Okay, so for respective section, respective region, liquid flow rate you need to consider. And here column diameter you have already started, you have already done. And following these two, wherever it will lie, okay, either here, let's say 2 meter diameter is there, it may lie here somewhere, it may lie here, wherever it will lie, that would be the liquid flow pattern you need to consider. Okay, and if you see over here, that value has been started almost I think 0.5. Okay, the reason being that below 0.5 or below 0.6, just nearby values, the what we can say that plate column is not feasible. Okay, plate column is not feasible for low diameters, low diameter column. So in that case, instead of instead of plate diameter, we will consider packed column. Okay, and that we will also discuss when plate column will be discussed. So there you will find that below 0.6 uh, meter, the plate column, sorry, pack column is more recommended in comparison to tray column. Okay, therefore this limit you can also see from here. Okay, so in this way you can find out the liquid flow arrangement. And next we will find out we will check the entrainment condition. That you can recall the last class: entrainment, weeping, flooding, backup, downcomer backup, all these parameters we need to check before proceeding further. Okay, so this entrainment, if you are considering, this entrainment will depend on the FLV, and you will consider only that FLV at which that tray is available, tray you are going to design. Okay, and these are basically percentage flooding. So let's say you have taken 80%, so you can choose this curve, or 85% just middle, and FLV value of that tray location you know already, so you can check the entrainment. However, that entrainment should always be less than zero point 0.1. Okay, entrainment should be less than 0.1, so it should not go beyond this. This is 0.1, right? Yes. So up to here, if your psi value, that is the fractional entrainment, that psi value you are finding less than 0.1, that would be correct entrainment. Okay, now if this condition will not met, what you will do? You need to decrease the flooding percentage. Okay, let's say you have taken 85% and somewhere here you are getting the value, so you need to reduce it to, let's say, 70% or 75%, like that, and then you can see the value. You remember flooding, that actual vapor velocity should be 70 to 90% of flooding velocity. 80 to 85 we consider as the optimum value. Okay, but you can decrease the value of flooding up to 70%, right? Now you can in this way you can check the entrainment. Next is the weeping condition, weeping point. Okay, so this weeping point is the minimum design vapor velocity, and that will be given by this. Okay, the minimum design vapor velocity should is given by this, and it depends on this K2, which is a constant, and DH, this is the hole diameter. Okay, sorry. And that UH is the minimum vapor velocity through the holes based on hole area. Then we are having hole diameter. Okay, then K2 is the constant, which we have already discussed. And K2 you can obtain from this. This graph is given, and on x-axis I am having HW plus HOW. Okay, HW is basically the weir height. Okay, however, HOW you can calculate by this expression 750. This expression you can take. Okay, here capital LW is the liquid flow rate of that region where plate is available. Okay, and LW is the length of the what we can say, the chord of the tray. Okay, the chord of tray. Just a moment, please. Here I would like to show the HW, but I guess you can understand that. And when we consider this LW, that is the chord. Okay, chord of plate. I hope you are getting. And or we consider as the wear length. That is the correct word. Wear length. Okay. Uh, LW is the wear length, and HOW is a wear crust. Okay, and capital LW is the liquid flow rate. So the point is, what is HOW physically? Okay, uh, just here. Yes. Okay. If you consider this this schematic, that is HW. Okay, that is HW, wear height, and HOW is what? HOW is when liquid is passing through this plate and moving down to this section, which is downcomer. Okay, uh, liquid will not come to downcomer section until unless it will not pass HW. Okay, so HOW is basically the what we can say, the height beyond H where liquid upper layer is available. I hope you are getting the point. Wear height is one thing. Another point is when liquid is flowing over the wear height, it must have certain thickness of the fill. Okay, so that HOW is that thickness. Yes. Okay, so in that way HOW you can calculate, which is called as wear crust. Okay, and wear length, I hope you understand that. How to find LW, small LW, that we need to discuss. And LW is basically the liquid flow rate. Okay, so liquid flow rate, when I'm considering to find out HOW, this liquid flow rate should be minimum. Okay, because more weeping condition we can have at the what we can say, when the liquid vapor velocity is very less and liquid flow is also less. Okay, in that way you can consider LW as minimum. And how you will find it, like in the last class we have discussed the maximum flow and the minimum flow that falls under turn down ratio. So turn down ratio you know already, a maximum flow is given, so you can find out this LW, capital LW. Okay, so in that way you can consider HOW, and then you can find out the UH. UH is what? UH is the vapor velocity at which weeping will occur. Okay, so minimum vapor velocity, whatever we are considering, that should not come below this. That should always be higher than this UH, right? So when we consider weir dimension, number one, weir height we need to consider. And how to choose that weir height? From 40 to 90 mm, okay, 1.5 to 3.5 inches. This is the weir height, okay, the complete range. However, more recommended value is 40 to 50 mm, okay. Now the weir length. Okay, the chord length will normally be between 0.6 to 0.85 of column diameter. Okay, so this chord length will depend on that how much downcomer area we are considering. Okay, so if I'm having 12% downcomer area, the weir length should be 0.77 into D. D for column diameter. Okay, 0.77 into D. Okay, and how we obtain this 0.77 from this graph. Okay, so if I'm having AD by AC, that is downcomer area by column area, that is around 12%. You can see over here, and you can find LW by DC. Okay, so that should be 0.77 into DC, LW value, right? So in this way you can find out, you can decide the column, weir height as well as weir length, and hole size that is given, uh, that is required to calculate UH. Okay, so the whole size used, uh, the whole sizes used vary from 2.5 to 12 mm. Okay, whole size you can vary in this range. However, 5 mm is most preferred or most recommended value. 5 mm, right? So you need to start with 5 mm. Weir height 50 mm you need to start with, and that LW, it depends on the downcomer area, so that it has nothing to do with the range. Okay. However, when we consider the whole size, we need to be cautious that whether fluid has fouling tendency or not. If it has, we need to choose the larger hole as the hole diameter or hole size. Okay. Further, typical plate thickness used are 5 mm for carbon steel and 3 mm of stainless steel. Okay, so that we usually punch the metal sheet and make the holes. Okay, or if you are considering beyond this value, this is the recommended value thickness. If thickness you are considering more than that, then you need to drill. Otherwise, up to 5 mm punching can be done easily. Okay, now next is hole pitch. Okay, hole pitch normal range 2.5 to 4 diameter, 4 times the diameter. Okay, square and triangular pattern are used. Triangular is preferred. and the total whole area as a fraction of perforated area is given by following expression for triangular pitch. Okay, so if you see here, I'm having the ratio of AH by AP. Okay, what is AH? Is the whole area, and this AP is basically the perforated area, right? And that is related with the term with the expression like zero 0.9 and dh by lp square or power 2. Okay, so from here you need to find this lp, because this lp is the whole pitch. Okay, dh you know already, you have fixed the whole diameter. Ah and ap you can sorry, AH you have already calculated, like 10% of active area. Remember, a few, like in previous slides we have discussed only. And AP is the perforated area which you need to calculate. In this parameter only AP you need to calculate, then you can find out LP. These two parameters are known. Okay, so in this way you can find uh, so in this way you can consider whole pitch. Okay, but still that calculation is not done yet. Okay, it is not completed. Once you know the AP, then only you will find LP. So we need to proceed towards perforated area calculation, AP. Okay, and as I have told you yesterday, we have discussed that there are four different areas. One is the column area, very commonly we know. Second is the net area. Okay, third, active area, and fourth is perforated area. Perforated area can be obtained by reducing the calming zone area from active area. Okay, so in this way you can consider. So recommended values of calming zone below 0.5 meter diameter, 75 mm, and above 100 and above that 1.5 meter you can have 100 mm as the column, sorry, as the calming zone thickness. Okay, so width of the support ring for sectional plates will normally be 50 to 75%. 75 mm support ring should not extend into the downcomer area. So that all these points we have already discussed. Like we have discussed in yesterday class that how plate is attached to the of the column, that will be through this support ring. Okay, and if in between also we have a plate in different, you can calculate that calming zone. Okay, because that calming zone, like different parts of the plate we can place side by side, and below that we have the backing strip, and because of that backing strip, hole cannot be made there. Okay, so calming zone includes what? Calming zone includes your uh, that uh, plane area of the plate just below the downcomer section. Okay, so that would be your uh, so that would be the calming zone, and this calming zone thickness that you have seen over here, that we can consider, and support ring also. Actually, right now we are only discussing the ranges and all. However, in the with the help of example, the method is more clear to you. Okay. So if you see here, I'm having this as column column area, and if you consider this is LW. Okay, this is LW, and then this particular section is called as the net area. Okay, and this is calming zone, this is calming zone, this is calming zone, and this is calming zone. Okay, so active area is this. Fine, this first line and this last line, between that active area is available. And this theta b is the angle which is made by this chord. As you can see, LW, that it is already here, and theta c, that chord is making to the center. Okay, and that you can find through this graph. So once you know all these parameter, by applying geometry you can find out the calming zone area, and that you need to deduct from the active area to find out the perforated area. Okay, theta c value you can consider over here. This is basically LW by DC. This is not capital L, this is also not capital L. Okay, this is a small l. So chord length or wear length by DC, that let's say 12%, for that we can have this value, okay, 0.77, and that we can consider over here to find out LH by DC. Okay, and when you consider this above curve, you can find out theta c value. Now what is this LH by DC? Okay, if you consider, if you recall the class where we have discussed AICHE method, okay, there you need to find out ZL. Okay, ZL is from inlet downcomer to outlet wear. Okay, that is nothing but the what we can say, ZL. Okay, so that ZL will how we have obtained that? We have already considered this parameter, this value from here to here by some assumptions. Okay, but this is the only graph through which you will make this LH value. Okay, so this should be a small LH. So whatever value we are getting, okay, that small LH by DC, it will give you the LH value. Okay, now in that way we can in that way we can find LH value, and that we will use in AICHE method. Okay, so you can find the calming zone area, and that should be deducted from active area to find the perforated area. Okay, now perforated area is AP. If you find that, you can go back to the previous expression. All are known except this LP. So this LP you can find out, and this LP should be 2.5 to 4 what we can say, diameter. So in this way you can consider this LP. Now this diameter belongs to what? This diameter belongs to hole diameter, not the column diameter. Okay, please keep in mind. So in this way we can find out hole pitch. Actually, I have a meeting right now. Okay, so this class we will stop here only, and we will continue the content in next class tomorrow, 11:30. Okay, only excuse me for today. I have a meeting. Fine. So we will continue the discussion in the next class. So thank you everyone for your patience. If you have any query, you please discuss.